Okay, so the next thing that we have here is basically the converse of the theorem that we basically stated in the end of the previous video, and that was basically what we said was that let x be a rational number whose decimal expansion terminates, then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to the power n times 5 raised to the power m, where n and m are non-negative integers. So now we want to know if the converse of this is also true, and the converse of this theorem would be basically if you have a rational number that in the form p by q, where p and q are co-prime, and the prime factorization of q is of this form, then whether that number, if that number can be, then whether the decimal representation of that number is terminating. Okay, so now the reason, and then it turns out that the converse, that this is also true, meaning that the reasoning for this is basically this way, meaning that let me go through the reasoning here, and the reason is basically quite simple. So here what we're saying is that we have a rational number in the form p by q, where p and q are co-prime, and the prime factorization of q is of this form, meaning that you have these factors of 2 and 5 in the denominator as q. Now where basically any rational number of the form a to b, if this is a rational number, and and if b is a power of 10, if this is a power of 10, it will have a terminating basically decimal expansion, because at the end of the day it's some basically integer divided by 10, and then you just keep moving the decimal point around, whether 2 decimal places or 3 decimal places, 4 decimal places, and so on and so forth. And based on this reason, of course, based on this reasoning, it's going to be always true. There is no case where basically this cannot work, except that basically, well, here we said that where m and n are non-negative integers, except that if, for example, let's say that for example either n or m is 0, okay, except that either n or m are 0 or both of them are 0, in which case you can actually do the same thing with the numbers. Let's say that, for example, the prime factorization of q is of the form of this form, where, for example, n is equal to 2 and m is equal to 0. So then you will have no factors of 5 in the denominator, and so as a result of that, of course, you will not be, and then as a result of that, your denominator is some power of 2 and not some power of 10. But of course it's easy to make it a power of 10, because you can always multiply the same thing by the denominator, multiply some factor of 5 by the, multiply some factors of 5 by the denominator, and multiply the same factors of 5 by the numerator, and then your denominator becomes some power of 10, and then you will be able to express that number in terms of in terms of some decimal expansion term, some basically terminating decimal expansion, meaning that, for example, let's say that you have a number over here and you have, for example, 3 raised to the power 2 times, for example, 5 raised to the power 2 over, for example, 2 raised to the power 3. Okay, so of course this number, whatever that is, you want to express it as a decimal number, basically as a terminating decimal number. It's possible, although the power of 10, the power of basically, although m is basically 0 over here, you have no factors of 5 over here, but you can actually add those factors in, meaning that you can write this as times 5 cube and then multiply the same thing over here, and then this becomes 3 squared times 5 squared times, for example, 5 cube, or basically whole over 10 raised to the power 3, because this is basically 2 times 5 whole raised to the power 3, and that's basically your numerator, whatever that is over here, divided by 10 raised to the power 3, which is equal to your numerator over here over 1000, and that means 3 decimal places. So then the converse of this is also true. And if you want to have a few examples here, I can also show you some examples. For example, if you have 3 eighths over here, so this is basically 3 raised to the power 1 over 2 cube. So you have some factors of 2 here, but you have no factors of 5 here, and you want to express this number as a and actually it's actually something interesting when you want to work with your numbers, right? So what you can do here is that you can write this as 3 raised to the power 1 over 2 cube times, for example, 5 cube, right? And since I have multiplied 5 cube over here, I can multiply 5 cube over here as well, and then I have basically 3 times 5 cube over 10 raised to the power 3, which is equal to 125 times 3, which is equal to 15, 1, 6, 7, 375 over 1000, which is equal to 0.375. So then there you can see that you have a terminating decimal, the terminating decimal expansion of this number. Or if you have 13 over 125, 13 over 125. So 13 over 125 is basically 13 is a prime number, but 125 is 5 raised to the power. So 5 raised to the power 3 is equal to 125, right? Now here I have 3 factors of 5, but I have no factors of 2, but I can add them in, meaning that I can write this as 5 cube times 2 cube, and then I can write this as 2 cube. I can add it over here as well, and of course you can always cancel them out. So then you have 8 times 13, so 13 times 8 over 125 times, for example, 8, and that's the same thing as 104. That's the same thing as 104, and 8 times 125 is 1000, and that's equal to 0.104, terminating expansion, terminating decimal expansion again. Or if you have 7 over 80, 7 over 80. So 7 over 80 is the same thing as 7 over 80 is the same thing as 80 is the same thing as 2 times 40. This is 2 times 20. This is 2 times 10, and this is 2 times 5. So this is 4 factors of 2 and 1 factor of 5. So I need another 3 factors of 5 so that I get 4 factors of 5 here, so I can have some power of 10 here. So I write this as 7 times 5 cube, and this is 2 raised to the power 4 times 5 times 5 cube. Okay, and then I can write this as 7 into 5 cube over 2 raised to the power 4 times, for example, 5 raised to the power 4, and then I can write this as 7 times 5 cube over 2 times 5 whole raised to the power 4, and that's equal to 7 times 5 cube over 10 raised to the power 4, and 125 times 7 is equal to 35, 3, 14, 17, 1, 8, 875 over 10 raised to the power 4 is equal to 10,000. So it's equal to 0.0875. And there you have a terminating decimal representation of this number 7 by 80. Which is actually very interesting. I mean, I never actually thought about. I probably did the same kind of thing before, but kind of I didn't really know what I was doing there, right? Or if you have, for example, some number like 14,588. 14,588 over, for example, I don't know, 625. So here again you need to prime factorize your I don't think you need to prime factorize your numerator. The denominator is enough. I think 25 times 5 is equal to 625. So that's 25, 2, 10, no. What is 125 times 5? It's 625. So 2, 10, 12, 1, 625. So that's, then 125 is 5 cubed, so that's 5 raised to the power 4. So this is 14,588, and this is 5 raised to the power 4. And then all I need here is basically 4 factors of 2. So I can write this as 14,588 over 5 raised to the power 4 times 2 raised to the power 4. I add these in, and I add them over here as well. And now I can write this as 2 raised to the power 4 is equal to 16. So that's 14,588 times 16. And that's 10 raised to the power 4. Okay. So now 14,588 times 16 is equal to 48,4. 48 plus 4 is equal to 48 plus 4 is equal to 52, 5, 30, 35, 3, 24, 27, 2, and 8, 0, and then you have 8, 8, 5, 4, 1, and then you have 8 over here, 1, and then 13, 14, 1, 12, 13, 1, 12, 13, 1, and that's a 2. So that's equal to 233,408 divided by 10,000, and that's the same thing as basically 23.3408. Okay, that's basically that. So you can see that any number that has that, so what we can say is that again, it's all about the converse of this theorem. It means that any rational number that can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to the power n times 5 raised to the power m, where n and m are non-negative integers. The decimal representation, the decimal expansion of that number is going to be terminating. And that's basically the next theorem over here. So now the converse of that theorem, you could write that as, for example, let x be equal to p by q, be a rational number, such that the prime factorization of q, such that the prime factorization of q is of the form 2 raised to the power n and times 5 raised to the power m, where n and m and n, we could say, are non-negative integers. Then x has a decimal expansion which terminates. That's basically this theorem. I call it theorem n, for example, n3, for example, something like that. Okay, so that's basically that. Now we have some sort of also rational numbers whose decimal expansions are non-terminating recurring, and we saw that in the example that I showed you. We saw that in the case of, for example, 1/7. So 1/7 is one of those numbers where if you actually do the decimal expansion of that number, so 1/7, for example, is a rational number, of course. But if you do the decimal expansion of this number, and let me actually do this again to show you how that, of course, although we did this already, but there is some interesting things here that I might not have mentioned about, for example, about this particular example or this typical example. So, for example, if you divide 1 by 7, what you will get is basically a 0 and then a decimal point of 0 and a decimal point over here, and then 1 times 7 is equal to 7, remainder 30. And then another 0 over here, another 0 over here. 4 times 7 is equal to 28, remainder 2. A 0 over here, a 0 over here. 2 times 7 is equal to 14, remainder 6. 0, 0. 8 times 7 is equal to 56. and remainder 4, 0, 0, and then you have 6 times 7 is equal to 42, 5 times 7 is equal to 35, and then you have a remainder 5, 0, 0, 7 times 7 is equal to 49, and then you have a remainder 1. And then again, if I add a 0 over here, 1 times 7 is equal to 7, remainder 3, 0, 0, 2 times 7 is equal to 14, remainder 6, I'm sorry, 3 times 7 is equal to 21, 4 times 7 is equal to 28, I'm sorry, 4 times 7 is equal to 28, 4 times 7 is equal to 28, and remainder 2. So what you can see, as you can see here, so I have the remainder 3, remainder 2, remainder 6, remainder 4, 5, 1, 3, 2. So it says 3, 2, so it starts with a 1 over here. So 3, 2, 6, 4, 5, 1, 3, 2, and so on and so forth. So the remainders over here, as you can see, are 3, 2, 6, 4, 5, 1, and the quotient over here is 7. The quotient over here is 7. So you have 1, 2, 3, 4, 5, 6, and then it just keeps cycling between these numbers over and over again, but it never goes above 6. It goes all the way up to 6 and then keeps coming down and then circulating in the same way. And because this block of remainders keep repeating themselves here, 3, 2, 6, 4, 5, 1, the same block of numbers keep repeating themselves over here in the quotient, 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, and so on and so forth. So all the way up to here. So then, for the same reason, we call the decimal expansion of this number we call the expansion of this number, we call it non-terminating and recurring. So it is, for example, 0.142857, a bar over these numbers, meaning that these will keep repeating themselves. And we call this basically non-terminating recurring. Okay, so and basically the denominator over here, as you can see, the denominator over here is not of the form 2 raised to the power n, for example, 5 raised to the power m, as we had in the previous theorem. It's not of this form. There are no factors of 2 here, no factors of 5 here. So then what that means is that based on the theorem that we had over here, that if you had for example, some rational number p by q where the decimal expansion where the prime factorization of q was of this form, then the decimal expansion of this number would be terminating. Then based on that, we of course, it's not right logic to based on that basically conclude that basically the the decimal expansion of this number, which doesn't have the same situation here, is going to be not of the same situation. Meaning that in this, what I mean to say is that in this situation, we said that if we had a rational number p by q, where p and q were co-prime, and then the prime factorization of q was of this form, then that the decimal expansion of this number is going to be terminating. Okay, is going to be terminating. Now, well, based on this, you can say that since this rational number, in this rational number, the denominator, or q, is not of this form, that the decimal expansion of this number is going to be basically not terminating. Meaning it's going to be non-terminating, and when it's non-terminating, it's supposed to be, it's got to be recurring, because the number is a rational number. Otherwise, if it was an irrational number, then of course the decimal number could not be recurring. Of course, I'm sorry if I mean, my senses were logically right, but I'm sorry if I confused you. So basically now, we could kind of, based on that theorem, say that the decimal expansion of this number is going to be non-terminating. Okay, but of course it's not right logic to do that, because here we have said that if we have this kind of situation, well, here we have said that here if we have this kind of situation, that the terminal, that the decimal expansion of this number is going to be terminating. But it doesn't necessarily mean that if for example the prime factorization of q is not of this form, that then the decimal expansion of the number is going to be non-terminating. It doesn't necessarily mean that, but you can kind of, I don't know, I don't really agree with that. Okay, it's basically somewhere in the text that I'm reading here. I don't really agree with that, but we can just go along with it, just to get to the theorem, right? So basically this kind of thing, this kind of behavior actually happens for any rational number. Not, I mean, based on the text that I'm reading, this kind of situation happens for any rational number not covered by the theorem that we just mentioned. So in the theorem that we just mentioned, meaning that, well, we might actually have to make up a new theorem based on the previous theorem, that if you have a rational number in the form p by q, where q is not of this form, that the decimal representation of that number is going to be non-terminating. And then based on that theorem, we could say that okay, so then based on that theorem, now you can see that the decimal representation of this number is non-terminating. But it's not necessarily stated in the theorem that we just mentioned. Okay? But as it turns out, anyway, I don't want to philosophize too much, but as it turns out, this kind of situation where the decimal expansion of the number is non-terminating recurring, it happens for any kind of rational number which is not covered by the previous theorem that we just discussed. Okay, meaning that if you have a rational number where basically the prime factorization of q is not of this form, then the decimal expansion of that number is going to be non-terminating recurring. So that's basically the whole idea here, and I'm sorry if I confused you. Okay, so now for this situation, I'm just going to write down this theorem and finish this whole thing. So the theorem is basically like this. So let x equal to p by q. Let x be equal to p by q. Basically, where p and q are coprimes, where p and q are coprime, be a rational number. Be a rational number such that the prime factorization of q of q is not of the form 2 raised to the power n, 5 raised to the power m, where n and m are non-negative integers. Where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating repeating. Or basically, technically we say recurring. Okay. So, and I think from the whole discussion that we had over here, you can conclude that basically there can be only two cases for the decimal expansion of every rational number. So, for any sort of rational number, the decimal expansion of any rational number it could either be basically this way, non-terminating repeating, which is also called recurring, or it is basically terminating. Okay, and while we are here, we can also talk about irrational numbers, and basically the decimal expansion of irrational numbers is always non-terminating, non-repeating. Okay, so for example, as an example, for example, pi, the decimal expansion of pi is basically 3.141519 and so on and so forth. It just keeps going non-terminating and non-repeating, meaning that there is no pattern that you can see in pi. It just keeps giving you different digits randomly, and of course it's not random in the sense that the word random is defined, but random in the sense that you cannot find any sort of pattern in the digits. The digits are just something like this. For example, let's say for example pi over here. So you can see that pi is equal to 3.1415926535898, and it's just, you can just calculate pi to any number of significant digits. For example, you could go for even for 200, 300 significant digits, 400 significant digits. You can do that using programs like, I don't know, I saw the other day on YouTube a gentleman had done it using Python, this programming language, and used the computer to calculate pi to, I don't know, like 100, 200 significant figures. So, but now the point here is that you cannot find any sort of patterns over here, and it just keeps going and never terminates. That's all about irrational numbers. And that's basically that. Okay. Now we have another theorem over here. I guess we can call this n. I will keep enumerating these theorems as, for example, theorem n. I don't know if it is 4, 5, or whatever that is. I will keep track of these theorems, and that's basically that. Now, if you are interested in exercises related to what we just talked about in these 2 hours, I will do a couple of exercises as well. So I'll see you in the next video. Thank you.